For this example, we're going to do a few things with this equation. We have y is equal to 3 to the x power. That is an exponential function. We have a variable up in the exponent. We're going to go through and graph that and then list out 7 other things: the domain, the range, the asymptotes, the left end and the right end behavior using limits, and also where the function is increasing and decreasing. To come up with the graph of this, you could go through and make an XY table, but if you're going to use parent functions with transformations to do this a little more quickly, here's the idea behind that. So to start with, our exponential parent functions are going to be in the form y equals a number raised to the x power. And in this lesson, all of our numbers here are going to be bigger than 1. So when that happens, when you have y is equal to a number raised to the x power, we can use parent functions to go through and come up with the graph. The parent function for all of the exponential equations that have a base of 3 would be y is equal to 3 to the x. The parent function for all of the base 2 exponential equations would be y is equal to 2 to the x power. This would be the parent function for all of them with a base 7. So you're going to have your different parent functions, and this base number, that is going to change depending on the problem. But there are some features of these graphs and all of the other ones, whether it's a base of 4 or 5 or 6 or 8 or any of them, that are in common. They all have some things in common. Here's what they will do. All of them are going to start out over here on the left side, just a little bit above the x-axis. And as you draw them in, they are going to slowly be getting higher. They're going to be increasing as you go from left to right. And all of them, all 3 of these graphs, are going to have a y-intercept at 1. And it doesn't matter if we're graphing y equals 5 to the x power, any of them. They're all going to have a y-intercept at 1. And then another point that's really easy to find is going to be 1 comma and then the base. So this equation is going to have a y-intercept at 1 and then go through the point 1 comma 3 because the base of the exponent is 3. This equation would have a y-intercept at 1 and go through the point 1 comma 2 because the base of the exponent is 2. This one, y-intercept at 1 again. They all have a y-intercept at 1, and this one would go through the point 1 comma 7 because the base is 7. So you can find 2 points really easy when you're looking at your parent function equation. All of them go through the point 0, 1, and then another point on the graph is going to be 1 comma and then the base. And they're all going to have this general shape. That's going to be enough for us to come up with the graph, but there is one more feature we're going to emphasize, and that is that there's a horizontal asymptote. It's kind of like a boundary line. Technically not part of the graph. The graph is what's in blue, but this boundary line does influence what the graph looks like. Basically, this graph is never ever going to cross down. It's never going to cross that boundary line. So we have a horizontal asymptote, and for all of these functions, for all of your parent functions for exponentials, that asymptote is right on top of the x-axis, and the equation for that is y is equal to 0. So from there, you should be able to go through and use transformations once you have this idea of what the family of exponential graphs looks like. You should be able to use transformations to do the graph quickly from there rather than going through and doing an XY table. Okay, so let's go back to this original problem now that we've talked about parent functions a bit. We need to come up with the graph for this. So let me make graph. All right. And then the parent function for this is actually this equation. There's nothing added or subtracted, which would be a vertical or a horizontal shift or anything. This is the parent function. So using that information that we talked about on the previous page, our parent function, it's going to have a y-intercept at 1, and it's also going to go through the point 1 comma base, and the base is 3. So this graph is going to go through the point 0, 1, and also through the point 1 comma 3, because the base is 3. And we're going to have a horizontal asymptote right on top of the x-axis. The equation for that is y is equal to 0. And then we know what the shape of this is going to look like. It's going to start out low and close to that horizontal asymptote over here on the left side, slowly be increasing, and then start increasing a little bit faster. So here is a very quick and good sketch for y is equal to 3 to the x power. Happens to also be the parent function for all of the 3 to the x equations. From there, we are supposed to list out and describe 7 different things. Domain and range and the asymptote are the first 3. Well, all of these equations are going to start over as far to the left as we can go, and they're going to be going to the right, and as we go to the right, they're going to continue to go upward and go to the right and up and to the right and up and to the right and up. This will continue going to the right for forever. The further it goes to the right, the steeper that's going to get, but it will continue going to the right for forever. So the domain is forever to the left and forever to the right. It is all real numbers, which you could write as an interval from negative infinity to infinity. In order for us to get the range, I would write down the asymptote equation first. That's y is equal to 0. And then for the range, our graph is either going to be above that asymptote or below the asymptote. So we can use y and 0 again, but in between, put either a greater than or a less than symbol. Y equals 0 is this line. Our graph is completely above it. So we're looking for bigger y values. So your range is y is greater than 0. So when you write down your asymptote equation for these exponential functions, you can, for your range, copy down the y, copy down the 0, and then in between will either go a greater than or a less than symbol. If your graph is above the asymptote, it's greater than. If the graph would be below, then it would be less than. Ours are going to be greater than. If you wanted to, you could put that into interval notation as well, rather than using the inequality. Okay. We have a couple of limits to write. We need a limit for the left end behavior and also the right end behavior. For the left end behavior, we start with LIM, and then underneath this we have to say, well, how far to the left does this graph go? This graph goes forever to the left, so x is approaching negative infinity. It's going forever to the left, and then as you go to the left to negative infinity, as you go to the left for forever, what is the height of your graph doing? What is y doing? Or instead of y, what is f of x doing? Well, our graph is getting closer and closer and closer to a height of 0. So there is a limit that describes the left end behavior. As you go to the left as far as you can go, the height of our graph gets really close to 0. Right end behavior. So again, we start with LIM, our limit. And this time we want to see how far to the right does this graph go. Well, it goes forever to the right. So underneath LIM, we would say x is approaching infinity. And then we need to describe what's happening to the height. Well, as you go to the right for forever, our graph goes up for forever. So as you go to the right, as you go to positive infinity, our graph goes up. It also goes to positive infinity. The height of the graph goes up and up and up. So there is the left end and the right end behavior using limits. As your graph goes to the left, it goes towards a height of 0. As your limit, as you go to the right, your graph goes up to infinity. The last thing that we need to describe is, where is our graph increasing? Where is it decreasing? For these two answers, one of these is going to be none, and then the other one is going to be your domain. These graphs either increase the whole time or they decrease the whole time, which means one of these is going to be none. It's not going to be both. It's going to be either increasing or decreasing. They don't ever do both. So one of these answers will be none, and then the other one is everything. So that is our domain. So one of these answers is none, and the other answer is going to be just a copy of whatever the domain is. So from negative infinity to infinity. When you do increasing and decreasing, start on the left side of the graph, go forever to the right and see what is happening. As you go to the right, from left to right, as you read this graph, as you travel along this graph from left to right, this graph is slowly going upward. It's slowly increasing to start with, and then it starts increasing at a faster rate. So this is increasing the whole time. As you go from left to right, the graph is always going up. So it's always increasing. So I copy down the domain there, and it is never decreasing. So that is going to be none for that one. We had y is equal to 3 to the x power. That does happen to be the parent function graph for all of the 3 to the x powers. So it went through the point 0, 1. We had a y-intercept at 1, and then 1 comma base for the other with our horizontal asymptote. And then from there, you should be able to fill in the 7 different descriptions that we are supposed to do.